Hi, my name is Anton and I'm a PhD student at the University of Bonn and a student researcher at Google, and today I want to present you an opinionated guide to node embeddings. And it's opinionated because there are many different node embeddings algorithms, and basically I picked some of them and I have some opinions about them, which are better, which are worse, which are more applicable and which are less applicable, and I will go through that with you today. So to summarize, there are many different graphs coming from various different domains, and they can be like social networks or biological protein interaction networks or transportation graphs, some citation networks and so on and so forth. And they're all very different, but we want some unified approaches to all of them. And there are different graph types. So for example, adjacent graphs can be directed or undirected. They can have weights attached to them or time steps attached to them or some like heterogeneous data attached to them. And this list is not exhaustive. So how can we model these things in a concise way so we don't drown in a huge number of different algorithms for very specific tasks? Moreover, there are different modalities that we can analyze in graphs. So for example, we can make predictions for nodes, we can make predictions for edges, we can make these predictions for small parts of graphs, such as subgraphs, or also called motifs if they're very small, or we can even analyze the whole graphs. And I'm sure there are people doing even more crazy stuff out there. And there are different tasks that we want to solve. So for example, we can do node classification or node clustering or anomaly detection or link prediction or graph classification and so on and so forth. I try to summarize all the different kind of aspects of graph mining in these 4 columns. And embeddings is really, to me, one approach of substituting the task, so very specific graph-specific algorithms, with tabular data algorithms. After we transform some parts of a graph, so most typically we transform nodes and assign them some low-dimensional embeddings. And this allows us to do tasks such as classification or clustering with the normal tools like k-means, for example, for clustering. And in this particular talk, I will focus on the embedding algorithms irrespective of the domain. I will not cover temporal or heterogeneous graphs, and I will only talk about embeddings of nodes, although I will also talk about how to do link prediction with those. So for example, for concrete example on how embeddings would help us solve a task. So for example, we have a clustering task at hand, so we would have a graph and we would want to obtain some clusters for these groups of nodes. But we want to do that through some learned representations. So we have some low-dimensional representation, then we would just slap k-means on top of that and get the same clustering output as we would have with a sophisticated graph clustering algorithm. In the same way, if we have some classification, so we have some unlabeled nodes and we have some labeled nodes here in color, we would want to predict the labels of the unknown nodes via low-dimensional representation. So for example, now we would apply logistic regression and get the labels for the unknown nodes. So I will talk about a lot of embedding algorithms today, covering from the first attempts to the most recent advances. I will cover in total 10 different papers, so please be patient with me. And I try to bring some unified structure towards that, and I will separate my talk in the 2 parts. I would call them first the neural wave and the factorization and sketching wave. So the second appeared a bit later, although the first paper in matrix factorization for node embeddings appeared in 2016. It was HOPE. I will talk, as I said, about 10 different algorithms, so I try to make a unified way how I talk about them. So typically, I want to present an algorithm via like a 1-sentence summary of the main idea behind it. And you can always find the real paper title and read the paper in the bottom left. And I will also try to make some illustrations about how the algorithm works for each and every one of them. So let's try and get started. First, I will talk about the neural node embeddings, and the first paper about that was a deep walk released in 2014 at KDD. It kind of revitalized the whole field, although of course the first paper proposed that was a bit before, but the field wasn't really that popular before the deep walk. So we will start looking at things from the deep walk family. And overall, the anatomy of the neural embedding is basically well-known word-to-vec algorithm for words. So word-to-vec, for those who do not know or forgot, is basically an algorithm to create a low-dimensional vector representations for words based on predictions of co-occurrences of words, simply speaking. And it was released in 2013. So the main idea behind the neural graph embeddings is basically that we have random walks on graphs, and the nodes in these random walks are somewhat related or can be thought as words in sentences in a natural language. So for example, here, if we have a random walk and we have a corpus of these random walks, we can, for example, select a node and use it as an input of a shallow neural network, also called self-supervised neural network. And we try to predict some other context node as an output of this neural network. And we basically have a representation for each node in the graph, like a low dimension, typically around 128 dimensions is used. And by maximizing the by minimizing the cross entropy loss, we arrive to some satisfactory representations magically. So the first algorithm, as I said, was deep walk in KDD 2014 by Brian. The idea is the very idea that started the whole subfield, is that nodes in random walks are approximately words and sentences. So basically we generate a corpus of random walks. So we start gamma in the paper, random walks of length t from each node. And then we simply use the pairs within some fixed window size W. In practice, we start 80 random walks from each node of length 80, so these are actually quite long, and use a window size of 10. So that means that we have quite a few, so like 6,400 times number of nodes, pieces of words. So if we actually want to store them, that's actually a lot of disk, but I will talk about that a bit later. The important thing about this algorithm in practice is that you never change W. So I know there are some papers that do that and set it to 5 or something. They really lower the quality of deep walk by doing that. And if you for some reason want to lower W, so for example, if you want to experiment, please increase gamma and t because these are two parameters, these three parameters are actually super interrelated. So if you lower W, you decrease training data a lot, and you need to remember that. Parameter meaning is not as trivial. So for example, it's not really obvious what to tune for the algorithm if you want, for example, more local representation. So the most trivial thing would be to lower W, but as I said, it lowers the training data set. So you need to increase gamma and t, and it's not really, it's hard to understand how to do that on a real graph. So talking about some practice things, there is an author's Python implementation that basically generates all the random walks, saves them on disk, and then calls word2vec on them. I wrote a slightly more efficient C++ implementation that does not store the extra walks, so you don't have to keep anything besides the graph in memory. The problem with this algorithm is that the optimization is g times log n at each step. So for large graphs, it can be a bit slow. And the practical limit on where it takes around a day to compute an embedding of a single graph is something like 3 million nodes graphs. And then we will talk about line. It's a 2015 paper from dub. It's a simplification of some sorts of deep walk, and basically they just try to remove all the parameters, so like W and gamma and T, and they basically say that you don't need to use them, you can just feed edges to the graph. Here, random edges from the graph are fed to the same neural network, but now it's optimized not with a hierarchical softmax of deep walk that gives rise to the log n update time, which is a bit slow. Now they use negative sampling with like 5 samples per node, which means that we have linear time complexity for each update. The algorithm is very simple and fast. It's not amazing on downstream tasks, but it is quite good if you have huge graphs. The important thing about the method is to set the total number of samples proportional to the number of edges. So in the implementation, authors use 10 billion samples for each and every graph, which is a bit excessive if we have small graphs that we want to try this on. And they have a marvelous C++ implementation that works really well, and the practical limitation for this method is approximately 10 million nodes, which should be enough for your pet projects and small tasks at home. Then I will talk briefly about Node2Vec, which is can be more widely known algorithm for node embeddings, even more so than DeepWalk, especially because it's a catchier title, and this is typically what you would Google instead of Word2Vec. If you think about, how do I apply Word2Vec for graphs? And then you say, okay, let's try Node2Vec, and you see the paper. The premise of it is a bit weird though. So they try to add 2 more parameters, P and Q, to DeepWalk. The rest of it is practically the same except for the negative sampling part. So the negative sampling is the same as a line, and the whole random walks, gamma random walks of length T, use pairs within window size W, is the same as in DeepWalk, but there are 2 more parameters, and I will show how they work. So I will focus on the walk generation part, because this is where the parameters are actually used. And the idea here is basically that these 2 parameters control second order random walk sampling. Second order random walk sampling basically means that we depend on the previous step of the random walk. Instead of just picking edge randomly, we use the information about the previous hop to control the random walk generation. And for example, if we start at the random node in the graph U here in the example, and we go to V, we go randomly because there is no information before. But now, if we want to go to a third node in this random walk, we have to consider second order information with the P and Q parameters. Basically, we have 4 candidate nodes to go to, U to go back, the red node on the bottom left, and 2 blue nodes. And we go back with the weight. It's not a probability per se, so the probabilities are normalized for each step, but it's 1 divided by P, and then going to the nodes that are 2 hops away from the previous node. So notice that blue nodes are not connected with the yellow node, U, so the weight of going to them is 1 divided by Q, and then the weight of going to the red node, because it's connected to the previous node U, is 1. So we have this array of 4 nodes, and we record the weights, and then we normalize them, so they're a probability, and we sample from them. And we pick, for example, to go back again, if the parameter P is low, we will go to the previous node with a very high probability. Then we generate this corpus of random walks, and as before, we train the single layer neural network with negative sampling on this corpus. There are 2 myths regarding Node2Vec that I want to debunk in this talk. So the myth 1 is basically that parameters P and Q are somehow related to breadth first search and depth first search in graphs. In reality, there is no way that you can have depth first search without memory. And the parameters P and Q are actually related to the triangles in the graph, which makes sense because basically, Q controls how much we go outside of the triangles and P controls on how much we go back. So if we have low Q, we go far away from closed triangles. So we basically try to run away from clusters as fast as possible. And with a high Q, we typically stay within triangles, or we even go back if P is low. Then we explore the information within tightly connected clusters. Myth 2 is that Node2Vec is a scalable algorithm. So it's even in the title, and typically we believe titles and papers. So the title is Node2Vec Scalable Feature Learning for Networks, published in KDD. In reality, the second order random walks are worst case quadratic in the number of nodes in the graph. And that's really bad if we talk about graphs. And the worst case is manifested on the graph that is shown here. If we have a star, it's called a star structure, then basically every second order random walk, because we have only these star edges, we need to compute the second order probabilities to all the other nodes in the graph, which means quadratic time complexity. In real graphs, because this is obviously a synthetic scenario, we have these problems, for example, in Twitter graph, where we have Barack Obama Twitter with a lot of followers, and their Node2Vec will fail miserably. The comparisons in the paper are actually misleading, so they use the lower number of walks per node for all method, which brings deep walk down quite a bit. And they do hyperparameter search for P and Q combinations. In practice, though, if you are not concerned with beating other algorithms with the worst parameters for them, please use gamma equal 80. And I have observed that tuning P and Q is not really beneficial in most graphs. There are some cases where it's not the case, but most likely, if you just need a good unsupervised performance, you don't need to tune P and Q. Again, as with deep walk, the Python implementation generates all the walks and dumps them to disk is super slow. Please avoid using that if you're really caring about performance. I wrote a C++ implementation that is a bit rough, but does the job. For larger graphs, as I said, preprocessing can be quadratic if your graph has a large degree, or uneven degree distribution with large maximum degree, you're out of luck with using this algorithm. Optimization is the same as line, though, after you generate the random walks. So it's OD for each step, or OND if you set the number of steps to be equal to the number of nodes. And the practical limitations is a bit rough because it depends on the pre-processing, but for bounded degree graphs, it's something like 500,000 nodes. If you're lucky, if you're not, it's like 50,000 nodes. Because of that problems, and because, it's still like a lot of parameters are, now we have even 5 parameters that we need to tune, and it's completely impossible to understand what the hell is going on. So I try to simplify, and I proposed an algorithm that was accepted in WWDAP 2018. It's called Verse. And the idea there is basically that we have been studying random walks a lot in graphs, and random walks define a similarity distribution among graphs nodes. So instead of using this random walks corpora, let's try to use similarity distributions directly. So what does that mean is basically that we have a similarity distribution defined by random walks. So the trick here is that we don't sample random walks to use in the neural network. We sample from the similarity distributions via random walks or some other way. For example, we can also sample edges, and then it's a meaningful similarity distribution between nodes. And then samples from that are fed to a neural network. And here, for example, we have the personalized PageRank distribution for nodes U and V, colored in yellow and blue in the graph. And we can see that these two are quite a bit different. So intuitively, we would have some separation if we learned a neural network to distinguish between those. And the total complete information about the similarity can be stored in the similarity matrix M. I will use it later in the talk, so pay attention and remember how it looks like. And here, for example, we can clearly see the kind of a cluster structure. So we have the last 4 nodes that were in blue. They're sort of like forming this yellow square on the bottom right of this matrix. But again, we do not use the full matrix, nor we never compute it. We just use samples from those, which are random walks. And why do we do that? Why do we have this like extra step of the similarity computation? Is that basically I was able to show that deep walk random walks are somehow doing approximately personalized PageRank of the graph. And that's important because personalized PageRank was studied a lot. It's used for scaling up some computations, and we'll later see perhaps how it's used to scale embeddings. And it provides intuition about the parameter. For example, for deep walks W, for large enough gamma and T, we can show that alpha of PageRank equals W minus 2 divided by W plus 1. And surprisingly, it's actually 0.83, I think, for default W equals 10, which is precisely the PageRank value, alpha value that was used in the seminal paper by Larry Page and Sergey Brin about the normal PageRank. The cool thing about thinking about the similarity part is that we can measure the quality directly because we know what similarity we want to use in the first place, and then we can measure how well it's reconstructed by the embeddings instead of, sampling and doing optimization but without any reasonable objective. And compared to deep walk and Notovec, I have 1 parameter instead of 3 or 5, which should ease life of the practitioner a bit, I hope. To advertise myself, I would say that it's a simple and fast algorithm, and other people have verified that it's really good for some reason on symmetric link prediction. Sometimes if edges information is asymmetric, it's worth using 2 matrices instead of 1. I provide the implementation in the GitHub repo, and optimization of overall thing is the same as line on Notovec, is OND. I think my C++ implementation works well. If it doesn't, please open issues and I will try to help you with that. And the practical limitations are kind of the same as with line. Approximately tens of millions of nodes. It works reasonably well on a single machine. So we covered 4 different papers for node representations. Now I want to take a different perspective and try to talk about factorization or matrix factorization based embeddings. And the basic idea of those is that we construct some similarity matrix between pairs of nodes, and then we decompose it. So for example, here I use the example of SVD, but we can use other decompositions, and we'll see that in a moment. To get some low-dimensional embeddings of the matrix that reconstruct it well. So the focus of the neural embedding was in prediction. Here the focus is on reconstruction. The first paper about this was HOPE, released in 2016 in KDD. And the idea there is basically that storing the whole similarity matrix M is extremely expensive. If it's a dense matrix, as we can see in the example, it's typically dense. We need a lot of memory. So can we do the decomposition implicitly with some sparse linear algebra solvers? So it turns out that yes, we can do that. And we construct the similarity matrix implicitly by using the adjacency matrix and then using some special form of SVD that decomposes matrices of form inverse of the matrix A times matrix B. And it turns out that 2 similarity measures, the personalized PageRank and the Katz similarity, can be used in this form. And it turns out that we can actually compute the factorization of such things very efficiently if we do that. So we basically compute the SVD, but we do not compute the similarity matrix of what we are doing SVD. That's quite smart. So basically the similarity matrix is implicit. It's never computed or materialized in memory. The problem with Hope is basically it doesn't really work well for downstream tasks. It is able to reconstruct the similarity matrix and the links in the graph, but it doesn't predict new links too well. It doesn't predict the node classes too well. The problem with that is the code is that it's like 1,000 of lines of impenetrable MATLAB code, half of commented, half of it is like uncommented, no comments. It's extremely hard to penetrate it. So overall, it's quite fast. So it works for graphs with millions of nodes on a single machine. The practical limitations is basically a MATLAB license or tens of thousands of dollars for that. But if you are able to get that, it can factorize graphs of, let's say, 5 million nodes in a matter of days. So the next algorithm is called AROPE, short for arbitrary order proximity preserved network embedding. The idea there is that we do not the SVD, but the eigendecomposition of the adjacency matrix of the graph. So adjacency matrix is sparse, eigendecomposition is quite fast on sparse matrices. And then we have the notion that if we have a function of a matrix, so for example, like cut similarity can be represented as a sort of sum of powers of the matrix, we can just apply the function to the singular value matrix of the graph. So just scale the singular values and then multiply and then sum together these things in an efficient way such that we get the approximation of the real similarity matrix. So the embedding is basically just a weighted combination of the eigenvectors Q of the graph and the scaled eigenvalues lambda. Again, the problem with that is actually doesn't work really well with node classification or link prediction. It is actually super easy to implement, and authors provide implementation in Python and MATLAB. Overall complexity is not amazing as Hope, but it's still nice. So it's just number of edges times d plus number of nodes times d squared. So that's typically the dominating factor. The actual speed depends on the eigensolver, so it will be a bit different in speed if you use it in MATLAB or Python, or if you use some like more advanced eigensolver for your graph. The practical limitations with the default author's code is something like 5 million nodes, but again, it doesn't really matter because it doesn't work well with the downstream tasks. So the next paper is going to address that in a slightly less scalable way. More importantly, it's a connection between the neural methods and the pure factorization-based methods. So the idea is actually quite simple. So when we do like random walks, in DeepWalk, we have implicit notion of similarity between each and every node. So we can count the number of ways, the number of times nodes co-occurred in random walks. And we can just analytically compute this quantity for small graphs. We can analytically compute this dense similarity matrix, and we can decompose it explicitly. So in DeepWalk's case, typically W is 10. So here I wrote a sum from 1 to 10 of powers of the transposed of the powers of the similarity matrix. And then we take an element-wise logarithm. So this is not a matrix logarithm, this is element-wise logarithm of this thing. So the matrix is dense, so it doesn't scale at all. The cool thing is that they showed theoretically that this is what DeepWalk does. The complexity is horrible. So the complexity of factorizing dense matrix, square matrix is cubic. So do not use it at home for graphs larger than 10,000 nodes. But it provided a great intuition of what we're really trying to do with neural methods. And there are ways to scale this sort of methods a bit further. They're not as efficient as the methods that we will cover next. And the methods we are covering now are sketch-based embeddings. So sketch is basically an approximation of the information that we would get. It's very similar to factorization in the sense that a sketch provides us some compressed information about the original matrix, but it doesn't really strive for exact reconstruction. So, and the main idea of the methods here in this category is that, kind of similar to the aerobe, we iteratively approximate higher order embedding, but we do not really strive for reconstruction of a very specific similarity matrix. So iteratively we would get from the sparse, kind of not reconstruction, but like what we would approximate is not an adjacency matrix, but rather a higher order matrix related to the graph. So the first method is RandNE, introduced in 2018. It actually does approximate higher order similarity matrix by doing iterative random projections, but I swear other methods do not approximate a higher order matrix. So we start by making like a large matrix with random values, and then we orthogonalize columns of this matrix. And then we iteratively multiply adjacency matrix by this, and then we get higher and higher order embeddings of the matrix. And then a final embedding is a weighted sum of these things. So typically we do this for 3 times. And for decent, so not good, decent downstream performance, we need to tune alphas. We need just 3 sparse matrix matrix multiplications. So overall complexity is really nice. And authors made a Python and MATLAB code available. Practical limitations of that method is basically an order of billions of nodes. The only downside is that we need to store all the UIs, all the embedding matrices, and when you have 1 billion nodes, I think the embedding matrix is something like 300 gigabytes, and you want to store that in memory for fast multiplication. So it's better that you have a lot of memory if you really do want to process huge graphs. This method is a decent thing to try. A slightly more modern thing is FastRP. So we start not with orthogonalizing the columns of a random thing, but just with a completely random matrix filled with this specific values. So square root of 3 with a probability of 1 divided by 6, minus square root of 3 with a probability divided and 1 divided by 6, and 0 otherwise. So 1/3 of the matrix are actually zeros. And the only difference to RandNE is that we iteratively set the next embedding by the values of adjacency matrix times the previous one. But we also introduced some kind of a degree normalization. And it turns out that this is what is needed to fix the problems of RandNE on the real world data. The final step is exactly the same. We have combined weighted sum with some weights that are set by authors by the parameters alpha and beta. We need 1 more multiplication than RandNE to work well in practice for whatever reason. The overall complexity is just dependent on the number of edges in the graph. The Python code is available and it's fast. The practical limitations are still the same. So kind of when you go this far in the scalability point, the main limiting factor is actually not the compute, but memory. And because you need to store all UIs, it's again approximately 1 billion nodes on a good server machine with, let's say, 1 terabyte of RAM. So the next method, and this is the last one, so we passed through 9 methods already, is node sketch. So, and now we come to the last method of a bunch, node sketch, the most scalable one, where we approximate high order similarity matrix by the iterative sketching. So we start by sketching for the Jacquard similarity the adjacency matrix plus the diagonal matrix of the graph. And then we iteratively resketch with some parameter alpha, which controls the decay. So alpha is something closely related to PageRank alpha, so something like 0.8 of A times the previous sketch, and we resketch, and the final embedding is not the concatenation or some reweighting of all the previous sketches, but simply just the last sketch that we have. And this is more efficient. So for good downstream performance, we need to tune the parameters again, but it's much faster to run, and we only need a couple of rehashes once more than in FastRP, but it's compensated by the memory advantage of this algorithm. And the practical limitations is, again, 1 billion nodes, just because we want to tune alpha for our particular graph. So we covered 10 algorithms, and now it's time for strong opinions about what algorithms should you use. And I think the choice is actually quite simple. It's all dependent on the scalability of the algorithms and how much do you want to weight versus the quality that you want to get. So if you have really small graphs, then it's probably a good idea to just compute something like netmf on your graph, just because it's so cheap to factorize these matrices. If you have like a moderate size graph, and this is something that we typically see in applications between 10,000 nodes and 1 million nodes, or maybe 10 million nodes if you can wait a bit longer, then it's a good idea to use deep walk. And deep walk here is with a star, because it's really a good idea to not use a hierarchical softmax with deep walk. So something like a node to vec with a p and q equals to 1, then it kind of degenerates to deep walk. Or you can just use my method, verse, that I tried to make as scalable as possible. Of course, the choice is ultimately yours, but I would definitely recommend switching away from the hierarchical softmax. If the graph is larger than tens of millions of nodes, something like 15, 20, 25, the random access memory problem of negative sampling starts to kick in. So every time we process a node, we start to fetch an embeddings of all 3 random nodes from the embedding table. And then if it's something like a couple of gigabytes, we have like huge number of these fetches. And this is actually what limits the scalability of these methods. So it's really a good idea to use some iterative sort of algorithms. And I would definitely recommend something like FastRP or NodeSketch for doing that. So we know how to do embeddings of nodes, so half of our problems are solved. I promise that I will touch on embeddings of edges, and basically the solution to that is surprisingly simple. For embedding of an edge between nodes U and V, which have corresponding embeddings A and B, we can just combine the embeddings of nodes to get a good embedding of an edge. And this works surprisingly well, for example, for link prediction. The problem here is that it depends on the algorithm, which one you want to choose. So for example, for deep walk, there is no better one, so you can just try all 5 and then select the best one via cross-validation. For verse, I've noticed that Hadamard product always works well. For node2vec, FastRP, Randony, blah, 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 you have to try at home. Typically, I imagine that the operator is, again, depending on the algorithm. Here are the 5 most used ones. I'm sure you can imagine some other ones that you can try. Please write me if you find something better. So overall, thank you for attention. Thank you for keeping with me for this overview of the embedding methods. You can always reach me out and find some new information, new tutorials that I make on Twitter. This presentation will be available on the website, and I will include the links to code and papers for all the papers we mentioned here. If you have some questions or just like concerns, or like you feel like you didn't understand something about these papers, you can always write me an email, and I will try to respond as fast as I can, but no promises there. And thank you.